I tried explaining this before, but I didn't like it. Hello, welcome to my channel. This is my very first episode, very first video. I'm gonna do math related content, but we'll see where it goes. And let's get started. My name is Matthew, by the way. If you look at my channel name, it's a little bit of a pun for you. Today, I wanted to show you what I to the I is equal to. So you can rewrite this as e to the ln of I to the I, just like that. Now the reason why you can do that, if you're wondering, if not you can skip ahead like a minute or so. If you have like y, and you have that set equal to e to the ln x, okay? And then you take the logarithmics of both sides, the logarithm of the ln of both sides, e to the ln of... The left-hand side stays the same, but the right-hand side, using your exponent rule for logarithms, you can bring this ln x out front. And this ln of e is just nothing but 1. So now you got ln of y is equal to ln of x. For this relationship to hold true, y must equal x, right? So when you look up here, let's say, because this isn't the exact form this is, let's say this is our y, and this is our x. All right? Now let's look. Y is equal to x. Okay, and this relationship stays true. Therefore, this relationship is true. Okay, so that's true. Bingo, bango. Take this I and the exponent out front into the logarithm. So now you're left with e to the I times ln of I. All right? So what's the ln of I? Well, if you think about Euler's exponential form for complex numbers, this guy, you can almost write as e to the I times theta, which is just Euler's formula, which is equal to z, the complex number. But in this case, our theta was ln of I, okay? So now what is the ln of I? So we have ln of I is equal to, I don't know, x. I don't know what it is. Or actually, let's stay consistent. Because ln of I was our theta in this guy, we'll say it's equal to theta. Alright, you can rewrite this as e to the theta equal to I. Alright? Because base e to the power of what it equals is equal to the argument. Now, I is of complex form 0 plus 1 times I, where the real part is just the 0 and the imaginary part is just 1. Now think about your complex plane, where you have your imaginary numbers along the y-axis and your real numbers along the x-axis. So, alright. So this is real, all real numbers, and this is just imaginary. I'm just going to put MIG for short. So right now you have a real number of 0, so you're right here along your x-axis. And now you have 1 for your imaginary axis. So you're like up here somewhere. All right? If you notice, this angle is pi by 2. So you can rewrite this again. If you know your exponential form, like Euler's exponential for complex number form, you can rewrite this imaginary number as e to the I pi. Because I is nothing but e to the I pi over 2, because you can see it on the imaginary plane. If you look at this relationship and this relationship, we have e to the theta is equal to e to the I pi over 2. To stay true, theta must equal I pi over 2. So theta is nothing but I pi over 2. Oh, So then the ln of I is just equal to theta, and theta is equal to I pi by 2. Sweet. I pi by 2. So we'll store that relationship up here. The ln of I is equal to I pi by 2. All right, we're almost done. So we can continue this over here. So if e to the I, and this, I'm going to replace this ln of I with I pi over 2, because that's what it is, that's what we found. So I pi over 2. And this is nothing but e to the, an I times an I is just -1. So you get negative pi by 2, which is a real number. Isn't that interesting? So in short, we found I to the I to be equal to e to the negative pi by 2. Thank you for joining this episode. I will have other content out. I'll hopefully go more into detail about if you're confused about what exponential form is. I'll show how to derive it later. I'll maybe talk more about the complex plane, because I don't know how high level people are watching my channel, but there you have it. I to the I is equal to e to the negative pi by 2. Wow.